Hello. Today we begin the discussion about ionic bonding. This is Mr. Crump. We're in Chapter 7 of Modern Chemistry. So if you're following along with your reading, Chapter 7. We have to think first about, before we get into how we name everything, a little background on how bonds form. Why do bonds form? Most elements are not stable as we see them on the periodic table. Most of them are going to gain or lose electrons to reach stability because atoms want a full outer shell of electrons, whatever that means. Some of them go through by losing electrons to take on a state that's stable, and some of them will gain electrons. And by doing so, they exhibit a full outer shell of electrons. They are stable, however charged. Okay, so if we think about noble gases, what do you remember about them from prior grades? You remember that they're stable, they're inert. Inert's a word that's used a lot. Inert means they are not likely to react, and they're relatively safe and to a point. And then that goes back into nuclear chemistry. When you get down here to radium, radium's unstable. It's above element 84, so therefore it is unstable all the time. But other than that, noble gases are inert, stable, with a full outer shell of electrons. They can exist exactly as they appear on the periodic table as gases all around us, and they're completely and perfectly stable. So that's what all atoms are trying to do, trying to exhibit. They want to have a full outer shell of electrons, but in doing so, they become charged. In other words, they have an imbalance of protons and electrons. Okay, and last unit we worked a little bit with protons and electrons and looking at ions. It's important to note that when these atoms are undergoing this change, all of a sudden they may have an imbalance and therefore have a charge. So what we're going to be looking at the first couple slides is barium trying to bond with iodine. That's why barium and iodine are there. And these are the elemental state of barium and iodine. No charge, zero. Strongly electric, this is why ionic bonds form. More specifically, why ionic bonds? Well, there's ionic and covalent bonding. In ionic bonding, strongly electronegative nonmetal atoms can take electrons from metal atoms. Metal atoms don't hold on to their electrons that are on the outermost shell very well, while nonmetals tend to be able to pull them away. When this happens, both atoms take on a charge, and that's why they're ions. And once they become ions, they're oppositely charged, and this attracts them together. When they do so, they attract in whole number ratios, and they form crystals. And that's because they're ions bonding. That's why we call it ionic bonding. And when I say crystals, I mean what looks like table salt. That is not table salt. I don't even know what salt that is, but that's an ionic crystalline solid. And so let's pretend it's barium iodide. What happens in barium iodide? Well, if we had barium and iodine in isolation, what would naturally happen is barium would give away its two outermost electrons, and iodine would take them. But you can see it's not going to work out in a simple 1-to-1 ratio because you would need more than one iodine to take both barium's electrons. So what happens is it takes two iodines. For every one barium, two iodines come along. Each iodine will take one electron. All of this abides by this trend that we're putting in our memory banks. The charge for each representative group on the periodic table and zinc, cadmium, and silver. So we have to know these. We have to put this table in our brain. So pause and copy if you want to. It's a good thing to do. When we write barium iodide as a formula, notice here, this is the final written format of barium iodide. We don't express a 1 here. Not necessary. So we just assume that since there's no subscript, that implies there is a 1. Binary ionic compounds are when there's simply one metal and one nonmetal involved in the bond. That doesn't mean there's just one copy of it. It just means that there's just two specific elements involved. The anion takes an electron or electrons from the cation. Metals form cations. Okay. And if you need a handy-dandy way to remember that, there's a lot of them. The one that my high school chemistry teacher taught me still works. He always drew a picture of a cat. Meow. And there's the cat's nose. some whiskers. But his cat was no longer alive. So he called his cat Cation. It's kind of a morbid analogy, but remembering the dead cats got pluses for eyes. Cation, metals tend to form cations. They give away electrons. So any positively charged ion is a cation. It's giving away electrons. While any negatively charged ion is an anion with a negative charge. In barium iodide, that's what happens. Barium gives away 2 electrons. 2 different iodines come and take them. So the steps to writing a formula, given a name. So assume I've been given a name, barium iodide. Determine the charge or the oxidation number on each ion. Monovalent ions are the ones we have listed in these columns. Okay, group 1 tend to be +1 charge, give away 1 electron. Group 2, give away 2. Group 13, give away 3. Skipping group 14 and skipping most of the transition metals. Group 15 tend to take 3. Group 16 take 2. Group 17 take 1. Those are your reactive representative elements. Notice we have a 0 here for the noble gases, but they're not reactive. So when we say multivalent, we'll speak about that later on. So monovalent cations are any of these you see in the vertical groups. So barium is here in group 2. So I know barium has got a positive 2+ oxidation number. And then our anion was iodine. It's in group 17. It's got a -1. So step 1, determine the charge of each ion. Step 2, write the cation's formula first, then the anion's formula second. And when we say write the ion, it's like we mentioned in video 1. Magnesium ion, and then fluoride ion. Okay. So step 1, determine the charge. Step 2, write the cation formula first, write the anion formula second. Step 3, write the charges above each ion. I've already done this on the prior slide. Step 3, write the charges above each ion. And step 4, crisscross or drop and switch. Now this is more of a physical method more than understanding, but if you understand that magnesium is giving away 2 electrons, fluorine needs to take only 1, it's going to take 2 fluorine. So the drop and switch simply means you take the number from the charge and you take it to the subscript of the other element, or the opposite element. So if we drop and switch, we get Mg1F2. And then we don't express 1s, and so it's just magnesium fluoride Mg(F2). Write the formulas for the following ionic compounds. So the method here on this table is not necessarily what you'll need to do, but in simple identification purposes, you're going to be going through this. Imagine a list of mixed compounds, not just ionic compounds that are plain old binary, but in a mix, you would say to yourself, I've got barium, which is a metal, and iodine, which is a nonmetal. This is an ionic bond. Calcium, Ca2+. Oxide is in group 16. It's O2-. In a 1-to-1 ratio, we bind calcium to oxygen. Now, you may hear us say, can we reduce that? And then the answer is yes. But you should simply see that you have 2 electrons being given away and the capacity to take 2 electrons, so it's a 1-to-1 ratio. So you would write it like that. This would be incorrect. Although true, incorrect. Magnesium chloride, very similar to magnesium fluoride we did a few moments ago. There's each ion written out. And then in dropping and switching, magnesium fluoride. Sodium nitride. Sodium symbol is Na. It is not S. Sodium symbol is Na. There's the charge. Nitride is not nitrite. Nitride is N3-. So, in expressing those 2 charges, I drop and switch Na3N. Now that's simply writing formulas. Let's look at naming. Naming is just as simple as it sounds. When naming ionic compounds, we're simply going to name the ions in order. We learned in a prior video that this is sodium and this is chloride. Okay, in a compound, this is ionized sodium ion, This is chloride ion. When we write the name, we write each ion by name. We don't write the word ion, just write the ions by name. That's all we have to do. Keep in mind that metal ions names are unchanged from the element's name. So Na sodium, Mg2+, magnesium. Non-metal ion names will change the ending of that element to "ide." Cl- is chloride, S2- is sulfide. Note that is "ide," not "ite." If you've memorized your polyatomic ions, you probably memorized several ites. And ites are not "ides." They are not created equal. In fact, let's write one. Sulfite looks like this. Sulfite. The similarity is an important distinction you have to make. It's an easy mistake to make on a test, and it can cause gigantic errors when we get further into the year. So differentiate "ides" from "ites." So we name the following, simply naming the ion. I've got calcium ion and fluoride ion. Calcium, fluoride. Is it fluoride or fluoride? It's not fluoride. Radium nitride. That's not nitrite. It's nitride. I'm here to help. Sodium and oxygen, sodium oxide. It's like falling downhill, isn't it? So you've seen so far in ionic naming that things are fairly straightforward. Hopefully that you see the relationship between charge and formula. If you have questions, please ask. That concludes the first video naming ionic compounds. Hopefully you've taken great notes with plans to come and visit again so you can solidify the learning with anything that gets cloudy. Please see us in tutorials or ask questions in class if any of this is unclear at all. The slightest question, write it into your notes now and visit with your teacher upon entering class the next day you see your teacher. Hope it's going well for you. We'll see you in the room.